All right, welcome to our next topic in our gas law unit, looking at the combined gas law. This just builds off of Boyle's, Charles, and Gay-Lussac's law with pressure, volume, and temperature, because most of the time all three conditions are changing, where the other laws always had something held constant. So in this equation, we have P1, V1, pressure and volume initial, all divided by temperature 1, is equal to pressure 2 times volume 2 divided by temperature 2. The only main thing we need to consider is temperature. We continue to want that in the Kelvin scale. Pressure and volume, the units there don't really matter as long as they are canceling or meet the requirement if a specific unit is requested for. Okay. So in this first setup, we have a helium-filled balloon. It has a volume of 50 liters at 25 Celsius and 1.08 atm. What volume will it have at 0.855 atm and 10 degrees Celsius? So again, the big thing here is recognizing units. Liters, I know, measures volume, and it's asking for what volume will it have. Therefore, my initial V1 is the 50 liters, and V2 is my question mark, what I'm solving for. Temperature, I know that Celsius is going to be a reflection of the temperature conditions that this is working at. And so the other thing with that is that T1 is 25 degrees Celsius, which is equivalent to 298 Kelvin. And T2 is 10 plus 273, so it is 283 Kelvin. If you want to show that work, you can, but you are not required to show the conversion of Celsius to Kelvin. Lastly, we have ATM. ATM is, again, a unit of pressure. So I know the starting and ending pressures for this system. P1 is 1.08, and P2 is 0.855. Looking at the overall setup then, I am building off of that P1V1 divided by temperature 1 is equal to P2V2 over temperature 2. I'm going to go ahead and start plugging in. And working on my second side, I have my 0.855 times my x all over the temperature of 283. Again, cross multiplying here to solve, I get okay. Working on getting x by itself. Work smarter here, not harder. And we're going to go ahead and divide by both variables. Okay. So then from there, let me snag a calculator real quick. You can type this in all at once. You don't have to do separate calculations. The big thing that'll be useful is just getting used to, again, putting parentheses on both the numerator and denominator here, just so you don't end up forgetting them in situations where you need it with the denominator. And help if I write in the 298 here too. So I'm dividing and then 0.855 times 298. So the numerator's in its own set, denominator's in its own set. I can keep 3 sig figs. I do have some rounding going on. So 60.0 is what I'm looking at there. Looking back at my units, what's going to end up canceling here is the atmospheres will cancel, and so will Kelvin. So this is liters, which if you think about it, we were finding volume. So that should make sense as a unit of volume. Here we have an unknown gas is held at a temperature of minus 158. And so the other thing is I do have a second temperature to work with here. I have minus 48. Again, this is the big reason why we use Kelvin with temperatures. So minus 158 plus 273 results in a temperature 1 of 115 Kelvin. Temperature 2, it was warmed to minus 48. So minus 48 plus my 273 gives me 225. And that takes care of the temperature side of things. It looks like it says it started in a container at a pressure of 60 atmosphere and talks about the pressure dropping to 50, or 30, not 50. Okay, so initially the pressure was 60 atm, and it ended with a pressure of 30. Okay, and it says by decreasing the pressure of 30, causing the volume of the gas to be 29 liters. And here it says how many liters of gas did I start with? Okay, so that tells me that I am solving for my initial volume, as where I know that I ended with 29 liters. Okay. So again, going off of P1 V1 all over T1 is equal to P2 V2 all over T2. Substituting in, and I had my V1 is my X, my V2 is the 29, T1 115, and T2 225. Again, we're going to cross multiply to solve. And then to get X on its own, we're going to go through division. So I take parentheses 115 times 30 times 29, close that in parentheses, and I'm going to swap out that subtraction sign that I hit and change that to multiply. There we go. Divide by 60 times 225. And it looks like I'm able to keep 3 sig figs, so 7.41. I was solving for volume 1, so liters is my unit there. Okay, so again, all it does is take our two laws that we've worked with and mesh them together. I have one last law that we're going to look at today, and that is Avogadro's law that looks at the relationship between volume and amount. It should make sense. The more of a gas you have, the volume is going to go up. It's going to take up more space. It's a direct relationship as well. Formula here is V1 over N1 is equal to V2 over N2, where N is the amount of gas. It's in a specific unit, just like temperature, and that we want it in moles. I'm going to just go ahead and skip to the second example. That kind of shows you the ins and outs of the formula and shouldn't leave you with hopefully too many questions. So here, to start, I have 6 grams of hydrogen. So I know that can lead me to my N, my amount. So the thing with that is that this is grams of H2. We need it in moles. So we need to convert it from grams to moles, and hopefully molar mass rings a bell. We know that the unit for molar mass is for every 1 mole, there's X amount of grams. If you go to your periodic table, hydrogen has a mass of 1. Formula for hydrogen is H2, therefore the molar mass of hydrogen is 2. So we have 3 grams, or excuse me, not 3 grams, but 3 moles of H2. And then from there, it asks how many grams of hydrogen. So we're solving for N2, which means we have all of our information then to find volume. It started with an initial volume of 32.8 liters, ends at a volume of 45.3. So using the equation that V1 over N1 is equal to V2 over N2, go ahead and plug in. We have a starting volume of 32.80 liters, and it has 3 moles of hydrogen gas. The new volume is 45.3, and that's going to be my X. So I'm going to go ahead and cross multiply and divide, and that result is going to give me N2. So I'm taking 3 times 45.3, dividing that by 32.8, and that gives me 4.14 with sig figs moles of hydrogen. it then requests grams. So then I just use molar mass to go back through. And that should give me, looks like 8.28 grams of hydrogen. Okay. And so that is our topic for today, just working with combined gas law and Avogadro's law.